my talk is really about tactile sensing and how can we build better sensors for a variety of different applications. So let's look at typical tactile sensing scenario. We have an object. We are trying to grasp the given object, and essentially our tactile sensors in our hand sort of give us, capture this information, and they give us some feedback how we should basically be interacting with these objects. So basically, we have tons of sensors in our hand, and basically what we are getting here is very dense tactile information from the sensors. Today, in HCI, if you look at the different types of sensors, they are kind of bulky, not exactly usable. So this is the current state of the art. In robotics, there's tons of different ways of effectively trying to perform the grasping. So for example, vision-based techniques are extremely important, and they are very prominent today. Lots of 3D sensors, cameras that are typically captured and that are coupled with current robotic systems to essentially guide these robotic systems. There are also a number of mechanical sensors that essentially allow you to capture the information. Typically, the sensor resolution is relatively limited in these cases. And then we also have the recent wave of optical sensors. You are going to see that talk about this later this afternoon. So this is also a very interesting technology that emerges in this field. Okay, so how our group tries to improve tactile sensing? So we have essentially came up with a new touch sensors, and we are striving to deliver the following three components. So first, the sensors needs to be high density. The second one, the sensor in our opinion should be flexible and stretchable, so it can be essentially applied to different types of surfaces. And then finally, it should be robust and durable. So basically, it should work in the field for extended periods of time. So these are the properties of the sensors that we would like to have. So this is essentially how the sensor that we have built looks like. We have tried many different things, and this is sort of what we have converged on. So in general, this, as you can see, this particular incarnation has 32 by 32 resolution. It's flexible, it's stretchable, and basically it allows you to measure the information for extended periods of time. So essentially what you are going to see from this kind of sensor is this type of map. So for example, if you apply the sensor to a human hand, you will see that the areas that have larger these sort of colors or larger circles that correspond to larger forces, the areas that are sort of white, that means essentially that there's little force essentially applied to these areas. So how is this type of sensor built? Well, basically, it's very simple. You effectively use a piezoresistive film that is inserted in between two different two different electrodes, conductive electrodes, and there is some protective cover on each sheet. So the architecture is embarrassingly simple that you have here, and can be really built from almost off-the-shelf components. This type of sensor can be built for less than $10. So this is really widely accessible. You can really start using it and building it. So this is how this sensors looks like. This is the data capture from the sensor. As you can see, it's highly flexible. It is, you can really, it captures the data through the set of wires. So building a proper connector in this case, of course, was pretty challenging. But then in general, sort of, if you try to sort of look at this type of capture scenario, this is the sensor mounted on a human hand, and in this case, the person is folding a paper plane. Over there, what is really, I think, the most interesting is sort of in the corner. It shows you the readout from the sensor. So in general, you can see as the person is manipulating with this object, you have this vast amount of data, tactile data that's being captured. Okay, so we also have looked at a number of these different properties. We have very carefully evaluated the performance of this type of sensor. This can sense the forces from roughly 30 millinewtons to 0.5 newtons, so this is a pretty good range. We typically repeat the sensor over thousands of cycles, so it's the repetitions and the performance doesn't degrade, and it has a pretty wide operating temperature, essentially up to 80 C. So this is a pretty wide range of temperatures over which this sensor can operate. We have also looked at the exotic designs of these sensors. What does exotic mean? It's basically, you can sort of cut holes within the given sheet, and in this case, the sensor can be sort of stretchable and easily can be stretchable, and basically the performance still stays the same. So this is how this sort of looks like if you cut out these sort of small exotic structures, and this sort of shows you that even if you pull on different sort of corners of this sensor array, that it still captures the quality of the data fairly well. So the summary so far. We have a pressure sensor that can be essentially, that is very inexpensive, very robust, operates over a wide range of temperatures, and basically we can apply this type of sensors to human hands and different types of robotic grippers. So the question is, can we, if we have this type of sensors, can we start combining it with modern machine learning techniques? So I'm going to show you a few different sort of applications. Obviously, I'll show you that we can combine it with machine learning, modern machine learning techniques. I would like to show you sort of this on relatively simple tasks. We would like to apply it to understanding how human grasps objects. So first of all, people can really perform simple tasks like, for example, classifications of the objects, or estimating weight of the objects, and we can do it just on the touch sensing alone. So I'm going to show you sort of that using modern machine learning methods, we can build computational models that basically can essentially perform these tasks almost equally well. So first of all, we have built very big data sets. So in this case, we have identified 26 different objects, and people were interacting with these objects, and effectively we have captured 130,000 of tactile frames for all of these object interactions. So this is how the typical interaction session looks like. As you can see, the participant is instructed to basically manipulate with the object, touch it from different sides, and sort of perform typical tasks with this object type. As you can see, kind of in a close-up, this is a very, very rich way of representing data. You can sort of see, the pressure maps directly, captured as the person is manipulating with the object. So what is the touch data representation here? Well, basically we have sort of, you can sort of think of this as almost having an array of, a two-dimensional array of data. So basically sensors locations are approximated on the 2D grid. And effectively, it almost looks like an image, right? So in the areas where you have data, you have basically, you can sort of essentially put it on a two-dimensional grid. And you can almost think of this as a two-dimensional image of all of the tactile information. And in this case, unused pixels essentially are set to 0 values. So how are we going to essentially to look at this type of data? We are going to use a modern neural network architecture. So this is a ResNet architecture that we have applied to this type of data. And multiple frames in this case are treated as sort of multiple sort of inputs to the systems. And then the output from this system essentially is a classification vector that tells us which type of objects we have interacted with. So the input is just the tactile information, these pressure maps, and the output is what type of objects we are interacting. So, and then essentially you get this kind of classification vector that tells you, and the highest value in this vector tells you which object it is. So let's look at some of the results. So this is the typical. The input would be some of these images, And the output in this case would be this vector that tells you which type of object we have interacted with. So if you look at this type of data, this neural network is going to tell you correctly in this case that we have interacted with the mug. So this is the correct object. If you look at another type of frame, in this case, the mug is slightly lower, but still pretty high, but slightly lower, but you can sort of see so that this is the correct object. But there are two other objects that are predicted higher. In this case, these are the Coq cans. So it's not really, basically the object, this neural network architecture does things reasonably well. Basically, it tries to predict very similar objects in this case. What happens when we extend it to multiple frames? Well, it works better, basically. You extend this architecture where more frames are fed to this type of neural system. And this just shows you that if you apply a larger number of frames, these touch frames, the classification accuracy goes is higher. And this sort of black curve shows you just if the object is essentially the best. This is the correct object. The red curve in this case shows you whether the correct object is within the best 3 predictors that we have that the neural network has essentially told you. So let's look at another sort of example here. So in this case, this is weight estimation problem. Same type of data. The person is sort of interacting with the objects, and in this case, neural network is supposed to tell you what's the weight of this object. So again, we have trained this data. We have trained the neural network on this data, and as you can see, in this case, the network predicts the performance or predicts the weight of the objects more accurately than just summing over all of the forces, and it's reasonably good compared to the ground truth. What is also very interesting is this is another extension of this work, is actually look at what the network is actually learning. So typically in computer vision tasks, people when they train these networks, essentially the lower layers of these networks learn special types of filters. So and these filters are pretty much learned completely automatically. In this case, we started with completely blank slate, and we wanted to figure out what do pressure maps that we captured, essentially, and the corresponding networks, what kind of filters do they learn? As you can see, the features that are learned from this data are quite similar to what typical networks for visual classifications capture and learn. So this is actually a very interesting finding. There are some small discrepancies between those as well. So the other sort of interesting questions are what is in the data. So what happens here is that when you capture pressure maps, you really in fact have a mixture of different forces. So one of them is basically object-hand interactions. The other one is essentially object signature, right? So this object interaction tells you the object signature, and there's also hand interaction. So hand basically the pose of this the current pose tells you something is embedded here in this data. So basically, for each type of frame, you also have a given hand pose signature. So the question here is, can we somehow decode this data? So in this case, as you can see, depending on the pose of your hand, you will see that the response of the sensor is slightly different. And what we do in this case, we are trying to decouple these two types of data, these type of information streams. Basically, the way to do this is to just look at the time of the captures, and we can, in this case, see. In this case, we can see that we can observe the whole stream of the data, temporal stream of the data, which tells you the data just before the object was grasped and after the object was grabbed. So in these cases, the pose really doesn't change, and the only thing that sort of changes is whether the object was grasped by the given hand. As you can see, we can, in this case, decouple these two data streams and essentially almost subtract the hand pose in these cases. What is also interesting in this data is sensor correlation. So if you sort of analyze all of these data streams of interacting with different types of objects, you will see that different areas of the hands are pretty correlated, and this is sort of embedded directly in the data. So we can run the analysis that tells you if you essentially if we are working with a given part of the hand, what are the other areas of the hand that sort of also help you there. So for example, if you sort of highlight on this sort of fingertips, you will see that other areas of the hand also help you sort of when you perform complicated tasks. So these are the other sort of areas of whenever you are touching something with this type of with the tips, the green areas tells you what are the other sort of sensors that typically, in this case, help you in this case. All right, so I would like to sort of summarize this talk. I have shown you how to build high-resolution tactile sensing that is inexpensive, that is robust, and operates over a wide range of different conditions. I also showed you how to build a machine learning workflow to utilize this data. And we believe that this new types of hardware and software opens many new different applications HCI, robotics, prosthetics, AR, and VR. I would like to acknowledge the colleagues that help us in this project and participated, of course, in this project. And I also would like to acknowledge the support from National Science Foundation and from Toyota Research Institute. Thank you, and this is the website where you can access all of the data about the project.